because you're behind time. Good morning. Okay, let's get back to our maxima and minima problems, our chapter 14.2. Let's take a look at try 7. We want to find the area of the biggest rectangular garden you can make with 36 meters of fencing surrounding the garden. So this is a rather realistic kind of question, okay, whereby in future if you want to look into like maybe the maximum area or the minimum packaging that you can have over a certain product and all that, okay, that's where our differentiation can come in very handy in making it a very efficient kind of calculation process. Okay, so if we were to just define certain variables to actually work with first, okay, so let us have area, okay, a variable for the area. So let A be the area of the garden. Okay, and since we have this 36-meter fencing, the fencing is going to be surrounding the garden itself, and that is going to make up the perimeter of the garden. So we can let P be the perimeter of the garden. Okay. We are looking at a rectangular garden. So the area is A, perimeter is 36 meters, in fact. Okay. When we talk about area and perimeter, we will need to involve our length and breadth as well. So let's also just define that. So okay, we let x and y be the length and breadth respectively as well. That would mean that we have x here and y here. Okay. So since in this case we have defined certain variables already, okay, and we know that 36 meters is going to make up the perimeter. Okay, so P is going to be 36, but perimeter is actually going to be made up by 2x plus 2y as well. So with P being 36, that also tells us that 2x plus 2y is equals to 36, and in other words, x plus y is equals to 18. So this is the first equation that we can actually form, right? Another equation that we can form is by making use of the area, okay, but there's no other information given about the area other than knowing that it's a rectangle, so the area will be length times breadth, so A is equals to xy. Okay? We are trying to find the biggest rectangular garden, and that would represent the maximum area. So with a maximum point or maximum value, our first derivative of it will actually be equals to 0, right? And then our second derivative, so first derivative, let's say dA over dx, will have to be equals to 0 because it is a stationary point, or rather more specifically a turning point. And then we have a second derivative, okay, and that will have to be lesser than 0. in order to give us a maximum, right? So, but then we have a is equals to xy, and we want to get the first derivative to be differentiating with respect to x. So we need to change away the y to make it in terms of x. And in order to do that, okay, we make use of our equation 1 over here. Okay, so we sub in 3 into 2. And we see that a is equals to 18x minus x squared. Okay. Now, why is it that I want to find a in terms of x? Why can't I do a in terms of y? You can also, okay, if you were to have a in terms of y, then your first derivative will be dA over dy, right? And there is nothing wrong with that, okay? But there is something wrong if you have x and y both together. Because in the equation itself, in differentiating, we cannot have two variables together. Okay, we cannot differentiate with respect to two different variables. Right? So we need to make sure that in our equation, okay, there's only one variable. Okay? Variables are things that continuously changes. Alright, so regardless of how x is going to be like, our y will have to change as well. Because we are limited by the fact that our fencing is only 36 meters long. Alright, so that is the reason why we want to change away the y to make it in terms of x. Although you can also change x in terms of y, then your derivative will be dA over dy and d2a over dy squared. Okay? So now that we have a is equals to 18x minus x squared already, we find the first derivative. That will give us 18 minus 2x. Okay, and then to figure out where is the stationary point, we find that x is equals to 9. So our length of the pyramid of the fencing, okay, or rather the length of the rectangle needs to be 9. Okay, but at this stage, we do not know whether it's a maximum or minimum. Okay, you must prove and verify that it is going to be a maximum. And in order to do that, we do our second derivative test. So differentiate this again, we find that the second derivative is negative 2, which is less than 0. Therefore, x equals to 9 gives maximum area. Question, keep in mind, we want to find the area itself. So when x is equals to 9, y would be equals to 18 minus x, which happens to be 9 as well. Okay. Therefore, area of the biggest garden possible will be 81 meters squared. In case you're wondering, how is it that the length being 9 and the breadth being 9 gives us a rectangle? Okay, please don't confine yourself to think that a square must be a square and a rectangle must be a rectangle. Although yes, sometimes you need to confine it. Okay, but sometimes rectangle is just in a very general sense, a more general idea. Okay, that includes a square. The square is more specific than a rectangle itself. Yes, Joseph? Sorry, I can't hear you. Will they ask this kind of question? Sorry, I can't hear the last few words that you're saying. Will they ask this kind of question where a particular area can fit inside the area can fit inside with the fencing. This one can fit inside the fencing, what? the area that you find surely will fit the parameter of 36 meters. Because how do you get your y and x relation? It came from the parameter itself. Yeah. I don't quite get what you mean. Yeah. Maybe if you encounter that question, then we talk about it again. Okay? Right, any questions? Okay, now let's move on to try 8. Okay, so we are given a right angle triangle ABC, base 12 cm, height is 5 cm. The rectangle BDEF with length x and breadth y is inscribed inside the triangle. Okay, we want to show that the area of this rectangle is being given by this formula here. Okay. Right, so we want to be looking at the area itself. So to start off, knowing that we have the shape, okay, this will be a rectangle, we can say that A is equals to xy, okay, because area is equals to length times breadth. But you notice that our area, okay, formula that we have over here is strictly in terms of x only. We do not have y involved, so we need to change away the y to be in terms of x. Okay, so our y is actually on this part over here. Okay, so we need to draw some relation to x. Since this is a right angle triangle, okay, maybe what we could do is to maybe think about Pythagoras theorem. Okay, that will be one way. But then, if you notice about Pythagoras theorem, we're going to be involving the hypotenuse. Okay. And if we were to involve the hypotenuse, then we're getting a bit further away in trying to draw any relation between y and x itself. You understand? Okay, so that means that Pythagoras theorem isn't going to be our basis to change our y into x. Okay, so what we will be doing instead, right, is that we can look at similar triangles. Okay, so what we can see is this is going to be a right angle triangle as well, since it's a rectangle. Okay, so we can compare this right angle triangle to be similar to the bigger right angle triangle. You understand what I'm saying? Okay, so that means that, okay, the ratio of the corresponding sides are going to be equal. So if you were to take this versus this part, okay, and this part versus the entire length, we can form an equation out of that. So that means that y versus 5 is going to be equals to fc, which is actually 12 minus x. Right? Because this is x and this whole thing is 12, so this part will be 12 minus x. And to the whole base of the bigger right angle triangle. Okay? Then after that I can cross multiply, or I can just multiply over the 5. So y is equals to 5 times 12 minus x over 12. Okay? And therefore, A will be equals to x times 12 minus x over 12. that's how we show the equation. Then in part 2, we want to calculate the value of x for which a has a stationary value. So likewise as what we did earlier, stationary value means that our first derivative will be equals to 0. And we want to verify that the value is going to make the area to be maximum. That means our second derivative test, it should give us a less than 0. Okay? But of course, second derivative test does not always show us that. Right? There are times that it doesn't tell us that less than 0. So if it's equals to 0, we have to still go back to first derivative test. But second derivative test is always slightly easier, okay, to handle rather than to do our first derivative. So looking at our stationary value, so we do our dA over dx. Since our a is 5 over 12x times 12 minus x, okay, what would you do, Li Hui? How do I differentiate this one? Five over 12. Then, sorry, say again. Sorry, I can't hear you at all. 5 over 12 then. Times 12 minus x. Then, plus negative what? 1 times 5 over 12x. That's all. Okay, so what she did was to keep the right side, differentiate the left, then after that keep the left and differentiate the right. Okay, so then after we simplify, in this case we get 5 minus 5 over 12x, negative 5 over 12x. So divided by 2, we have 5 minus 5 over 6x. Okay, so dA over dx is equals to 0. Our x is equals to 6. So that answers the question for the first part that asks for the value of x for which a has a stationary value. So you may want to write a concluding statement. A is a stationary value when x equals to 6. Then we want the a to be a maximum, so we got to do our second derivative. And by differentiating the first derivative, we see that the second derivative is less than 0. So therefore, a is a maximum when x equals to 6. And we have shown that. Okay, next we look at try 9. So in try 9, we have to find the coordinates of the point on the curve y equals square root x. That is a minimum distance from the point 90. Okay. So if you don't know how the curve looks like, usually we just anyhow draw one curve. Okay. But I thought that maybe it would be helpful if you know how does this y equals square root x looks like. Okay. In the previous syllabus, actually this was part of the syllabus to learn what is the shape of y equals square root x. Okay, but to actually very quickly know how this shape is like, right? Do be aware that y equals to square root x means that we can actually square both sides, right? So y squared equals to x, right? We know the shape of y equals to x squared, right? Y equals to x squared has the shape of a quadratic curve, and it intersects at the origin 0, 0. Right? So our x-axis is here, y-axis is here. But now we have y squared equals to x. So it seems that there is a reverse in our x and y-axis. Okay? So therefore, our y squared equals to x curve would, in fact, look like this. Okay? So it is just a reverse of your, this is still your x-axis, this is still your y-axis, just the other way around. Okay, so this is how your y squared equals to x looks like. But if you're looking at y equals to square root x, since this square root is a positive square root, okay, so that means that our y values are always positive for whatever x values that can be. But in this case, x values can only be positive. So this is our y squared equals to x, but our y equals to square root x essentially only half of it. Okay, sorry. Okay, so this is how our y equals to square root x looks like. Alright? I believe in your textbook the example also has given you the shape of the example question was rather similar to this one, if I recall correctly. Oh, it didn't. Sorry. Okay. But anyway, so y equals square root x is this way. It will be helpful to answer this question. But if you don't know, never mind. You just need to understand and follow through with the question itself. So we want to find the coordinates of the point on this curve. Okay, so at some point, there is a minimum distance from the point 90. So 90 is on the x-axis since the y coordinate is 0. So let's say if 90 is here. Okay, we want it such that this distance is going to be minimum. Okay, so even if you don't know how the curve looks like, even if you draw something like that, just have to draw x-axis to understand this is the idea that we're looking at. Right? So, since we're looking for minimum distance, let this distance that we're trying to find, okay, between the curve and the point 90, let it be d. So let's just define that. That distance between 90 and a point on y equals to square root x be d. Okay. For any point that's going to be found on the curve itself, if I know the x coordinate, let's say it is x, then the y coordinate value will definitely satisfy this equation, which is square root x. Right? Okay, so that means that the distance d, since I know this coordinate and I know this coordinate, I use the length of line segment formula. That will be square root of difference in x coordinate, so x minus 9 square, plus the difference in y coordinate. square root x minus 0 square. So that's how we form the equation. Then we can simplify it. This is square root x minus 0 bracket square. So it actually simplifies the square root x. You square it, you will get x, yeah? So our expression for D is our square root x squared minus 17x plus 81. Okay, so that's when we next go on to find out what is this minimum distance. Okay, so to find the minimum distance, we figure out the first derivative, make it equals to 0, figure out the stationary point first, then after that we verify that it is a minimum by doing second derivative test. Alright, so could you please do that now? Alright, I give you about 5 minutes. Find your first derivative and your second derivative. Figure out the x value. Then you can figure out the second derivative, whether is it going to be giving you minimum. So find dd over dx. give you another 2 minutes. Derivative test is going to be very difficult because you don't know how to differentiate, then please rely on your first derivative test. It will save you some time and save you some trouble. Shall I run through? Generally, I think most of you can do your first derivative. Okay, so your d could be expressed in this manner. Okay, so first derivative. On hindsight, maybe I shouldn't have let the distance be d, so that I avoid having dd over dx. Okay, which is a bit confusing. So I bring down the power, then after that x squared minus 17x plus 81. Power minus 1, so I get negative half. Differentiate the inside, I will get 2x minus 17. Most of you are able to get, for me, 2x minus 17 over 2 square root x squared minus 17x plus 81. Okay, then we want to find out the stationary value. So that means that our dd over dx equals to 0. Okay, so actually we can cross multiply this, our denominator would be gone. So our x would be 8.5. Okay, so this will tell us x is going to allow us to have our distance to be a stationary value. We do not know whether it's a maximum or minimum at this juncture. So we need to proceed on to figure out whether is it minimum or not by using second derivative test. Okay, so I'll show you by doing the second derivative test first. It will be challenging to do by second derivative test. Okay. So in this case, maybe it will be easier if you want to do by product rule, or if you want to do quotient rule, that's also fine. So let's do our quotient rule, let's say. Okay, so I keep the bottom, differentiate the top, I have a 2, minus away, I keep the top, differentiate the bottom, so I will have a 2, bring down power half, x squared minus 70x plus 81, power minus 1, differentiate the inside. Okay, so that's all in the numerator. Denominator, we'll have to square it. Okay, so simplifying it, this cancels out. Okay, since our objective over here is to check whether our second derivative will be more than 0 or less than 0. Okay, if you think that you want to press your calculator in this kind of format, then so be it. Okay, maybe you want to neaten it up a bit and press it in this format, that's also fine. If you want to neaten it up further, that's also perfectly fine. Okay, but do be very careful as you try to neaten up the whole fraction. Okay, in trying to get your calculator pressing to be easier, you got to make sure that your neatening up process, okay, is actually correct. If it's wrong, then surely your answer will may not be actually accurate anymore. Okay, so you may want to just stop it here. Then after that, you press in x equals to 8.5 into the calculator using this form. You should be able to get about 0.33806. Okay, and that is going to be more than 0. Okay, right? If you find that you're very stuck, okay, in trying to do the second derivative in this kind of question, then by all means, please go and do your first derivative test rather than having to risk errors in your calculations. So x and then after that sine of dd over dx and your tangent. So we do 8.5, 8.4 and 8.6. Okay, I believe it should be this way, negative, then 0 and positive. Okay, so then after that, you will be able to prove that x equals 8.5 gives you the minimum distance, but the question wants you to find the coordinates on the point. Alright, so that means that x is 8.5, your square root x will be square root 8.5. So therefore, coordinates of the point is 8.5 and square root 8.5. If you want to keep things in exact, okay, okay, so this should be the answer. Otherwise, what are you suggesting? What are you thinking about? Sorry? This is exact one. Exact value. Square root 8.5 is an irrational number. 3SF, okay? You can leave it in 3SF as well. Alright? Nothing wrong with that, okay? But sometimes I prefer to leave it exact lah. Okay? Any questions? Okay, if no questions, then that's all for chapter 14.2. Homework. I mean, what else can you expect? Question 5, 8, 9, 11, 13. Due on. This is our even week. Due on Thursday. Okay. Questions? Alright, next we are going to move into chapter 15. Okay, now that we are going to chapter 15, I strongly urge you to actually make sure you have your formula booklet with you, alright, so that you can remember it and practice it. Okay, because we are going to be looking at differentiation of your trigonometric exponential as well as your logarithmic functions. Okay, so we have been looking at differentiating algebra. We will first be looking at differentiating trigo functions. Okay? So when it comes to differentiating trigo function, we fall back on our understanding of differentiating. Okay? Where we understood differentiation, or rather the first derivative. Okay? The first derivative tells us the gradient of the tangent of the curve. Okay, so for scientists, right, they look at the gradient of the tangent of, let's say, a sine curve. Okay, and then after that, they try to piece up all the information they have regarding the tangents, and they discover that the gradients itself, okay, form a cosine function, and that is why the differentiation of your sine function is going to be cosine x. So by similar process, the differentiation of cosine x, take note that it is actually negative sine x, and the differentiation of tangent x, tangent is always the odd one out, will give you secant square x. Okay, so this is 3 important formula that you must remember. Okay, so do recognize that when we introduce our trigonometric functions or exponential or even logarithm later on, okay, our product rule, quotient rule, all the problems that we have tried in terms of your increasing, decreasing function, maxima, minima values, they will all apply as well. Okay, so you cannot see this in silo, okay, you cannot see this as standalone, different from your other, the earlier chapters. Okay, so in trying to differentiate our x minus 2 sine x, what we are going to get is that we differentiate x, we get 1. Minus 2 sine x, 2 is like a constant, so we can ignore that, okay, but it still remains up. Then we differentiate the sine x. Differentiation of sine x gives us cosine x. So it entirely disappears, okay? So sine x disappears and then replaced with cosine x. Okay? So this will be the differentiation of x minus 2 sine x. Then in the differentiation of x plus 1 tangent x, dimension product rule applies. So we keep the left, differentiate the right, which is tangent x, that gives us secant square x, plus keeping the right, differentiate the left, which is 1. So this will be the answer. And in part C, to differentiate our cosine x over x, we can also use our quotient rule, e over x. Okay, we can apply our quotient rule as well. So keep the bottom, differentiate the top, which is the cosine x that gives us negative sine x. Minus away, keep the top. Differentiate the x at the bottom, we get a 1 over x squared. So simplify this. We have negative x sine x minus cosine x. Since there's negative on both of the terms in the numerator, we can take it out to be at the center in the sense of factorizing. So we get negative x sine x plus cosine x over x squared. Okay. Now what if, instead of saying sine x, cosine x, and tangent x, we have sine 3x, cosine 3x plus 2, and tangent 4x minus pi over 3. Okay, so our idea of chain rule applies. Okay, so differentiating sine 3x. Sine itself, when you differentiate, it changes to cosine. Okay, so cosine what? Cosine 3x. Okay, then after that we need to differentiate the things found inside the function itself. So that means differentiating 3x, we get a 3. So we get 3 cosine 3x. Okay. Alright, then part B, we want to differentiate cosine 3x plus 2. Okay, we maybe give it a try. Nicole, what do you think is going to be? Differentiate cosine becomes? If I differentiate cosine, what does it turn out to become? Negative sine. And the things inside, that means the angles, that will be 3x plus 2, followed by, times 3. Okay, so we differentiate our 3x plus 2, we get a 3. So to simplify this, we get negative 3 sine 3x plus 2. Okay. Then one last one, differentiate tangent 4x minus pi over 3. Okay, answer, what do you think? Differentiate tangent, we are going to get secant squared Now, bracket 4x minus pi over 3. Okay. Times 4. That's all? Right? Very good. Okay, so differentiate tangent, change to secant square. Then differentiate the inside, we get a 4 on the outside. So, by convention, we usually write it in this method. Okay? Alright, I'll just stop here today. Let this go and sink in. Then tomorrow we're going to do more.